Now comes a relatively tricky video wherein we walk through how to assign R and S for any stereogenic center. Now, I've already worked through this before on a previous video. I've told you what the answer is, but the process by which I did it, I'm going to walk through now. And there's actually two different ways of doing it. There's the one that's in your book and the one that I'm going to outline here. And then there's the way that I actually do it, which involves using my right hand because I'm so right-handed, and can involve using your right hand and your left hand, depending on your preference. Keep in mind, again, ring means left hand, but I'm going to walk through the first part of the video with the flipped version of it so that I can just draw things that make sense to me and talk about it. And then when I go to show you the hand trick, what I'm going to do is flip it so that you'll be able to read this text instead. So right now, hopefully, everything looks normal. You can read all the text up here. And what I've done here is list for you the algorithm by which you figure out the R and S, assign the stereogenic center. So first, you need to identify where the stereogenic centers are in your molecule. And the key thing is to recognize that a stereogenic center must have four things bound. Now, if you're not sure, start by trying to assign the Cahn-Ingold-Prelog priorities, 1, 2, 3, 4. And what you'll find is if they are tied, then it's not a stereogenic center. So if I were to come up with, say, 2 hydrogens on an atom, then I'm going to have a tie at priority 3 or something, priority 4. So in any event, you can start assigning Cahn-Ingold-Prelog priorities, and that will tell you, hey, do you have 4 unique things? Assuming you have 4 unique things, then what you do is rotate in such a way that the molecule has priority 4 pointed away. And right now, this isn't true. We'll talk about that in a second. And then once you've done that, then a clockwise rotation among the others is an R stereogenic center, and a counterclockwise rotation would be an S. So those are the algorithm procedural steps that you need to follow, but let's assign these guys. So the key feature of the Cahn-Ingold-Prelog rules is that the highest atomic number, which is to say the heaviest atom, essentially the biggest atom, is going to be higher priority. And there is a case where it's not obvious at the first because you've got a carbon bound to another carbon and so on. And so at the first point of difference, then you would make the assignment. Although here, what I have is a carbon atom that has 4 different atoms bound to it. So we're not going to need to invoke the second rule. There are plenty of cases where you're going to have several carbons bound, and then you need to keep going until you decide later. So highest atomic number at the first point of difference is how you assign priorities. Okay, so what are the priorities here? What's the heaviest atom? What's the atom with the highest atomic number? Well, it's going to be bromine is heavier than chlorine, which is heavier than fluorine, which is heavier than hydrogen. So in other words, priority 1, priority 2, priority 3, priority 4. Likewise, for this carbon atom, all I'm doing is looking at the atoms that are bound directly to that carbon atom, and I'm starting to assign them again via the highest atomic number. So the highest atomic number would be the bromine, which is heavier than chlorine, which is heavier than fluorine, which is heavier than hydrogen. And there you go. Okay, so next we need to rotate the molecule, pick up the molecule and rotate it in such a way that the lowest priority group, which will be a hydrogen if you have it, is pointed away from us. So right now, this hydrogen is pointed up. So what I need to do is actually rotate it so that it is pointed away. So I have learned to my great chagrin that I am not capable of teaching certain aspects of stereochemistry with the LIGHTboard. I have too much trouble with the thing I'm working on being between me and the audience, so I really need to have this orientation. You sitting over there, me working right here, and so that we can orient things well. So for example, one of the things I'm trying to do here is show you how I rotate this structure to end up with the new structures. And what I'm going to do is I'm going to take this hydrogen that's straight up and down, and I'm going to push him back into the board. And so you can see that what I'm doing is this rotation 90 degrees. I would illustrate that by saying, here's the axis on which I'm going to rotate, and I'm going to rotate around that axis 90 degrees in that direction. So we're going this way. Once I've completed this rotation, then we can go back to the LIGHTboard and it will work just fine. But for now, this is the rotation that I'm doing. Okay, so the bromine then, which is coming toward us, ends up vertically up. So Chem3D, being a drawing and visualization software that I have available to me, allows me to show you the rotation I mean in real time. So to orient you, this white atom is the hydrogen, this yellow atom is a fluorine, the red is the bromine, and the greenish is the chlorine. And so I'm kind of lying to you. I'm not actually just doing a 90-degree rotation. that would end up putting the bromine off axis a little bit to the right. So not only am I rotating 90 degrees like so, but I'm also rotating slightly in this direction so as to end up with something that's easy for me to do. So anyway, that's what I did. I basically rotated 90 degrees in this direction with a little bit of a twist to put the bromine straight up and down, whereas it should have ended up cocked to the side, maybe 30 degrees or so. Then I'm going to do the identical thing with the mirror image as well. The fluorine is largely unchanged. The chlorine is largely unchanged. All we're really doing is rotating this so the chlorine comes into the plane, and then the hydrogen ends up back away. On the far side of this mirror plane, we're going to end up with the exact same thing, but let's walk through it. Force this back again. The bromine is going to end up vertically up. The fluorine, which is pointed away, down and right, is going to stay there. The chlorine, which is down and toward me, stays there. And then the hydrogen is again going to be back away. And because I have this mirror plane, I'm going to show it on the far side, kind of going back up away. But it doesn't really matter, because the whole point is that the hydrogen is then into the board. So once I've done this rotation, now it's possible to go back to the LIGHTboard for a bit and continue on with the analysis there. We'll return here when it's time to teach you the right-hand trick for how to do these assignments. Now that I have this drawn the way it is, with bromine, chlorine, fluorine, and hydrogen pointed away, then this rotates to the right, therefore this is R. And again, this would be R. Here, this rotates counterclockwise, therefore from 1 to 2 to 3. Therefore it's S, which means that this original group is S. And that's how this is done. Okay, so it's a bit of a wasted effort to do this. On the other hand, reinforcing how to assign priorities is always a good thing. So the key thing to keep in mind, of course, is that the heavier the atom, the higher the atomic number, that's going to make it priority 1. So bromine is going to be priority 1 because it's bigger and heavier than chlorine, which is priority 2, which is bigger and heavier than fluorine, which is priority 3, and then the hydrogen is 4. Of course, that analysis holds right here. 1, 2, 3, 4. And likewise, the assignment of priorities doesn't change no matter how they're oriented in space. As long as I have bromine, chlorine, and fluorine, bromine's always going to be 1, chlorine's always going to be 2, fluorine's always going to be 3, and hydrogen is going to be 4. According to the analysis we did on the LIGHTboard, if you have 1, 2, 3 oriented this way, which is to say clockwise, then that then makes this an R for assignment purposes. It is right-handed, whereas counterclockwise, this direction would make this an S as long as the hydrogen is oriented back away. So far, so good. There's nothing complicated here. Now, the point of what I'm about to show you is to avoid the necessity for rotating the molecule like we did. Originally, this hydrogen was neither toward us nor away from us, so in order for us to assign its priority, assign it R or S, we need to rotate so priority 4 is back into the board. So that's what I did with that rotation. However, if you learn how to use the right-hand trick, or possibly the right and left-hand tricks, depending on how you prefer to do things, then you can go ahead and assign things the same way, whether they're oriented well or oriented relatively poorly for you. Okay, so the way this works, you want to align your thumb either with or opposite the H. Either with or opposite priority 4 if you're going to use the fully right-hand trick. But the idea is that I want to have my fingers aligned from the carbon toward priority 1. So I'm always trying to analyze this carbon, so what I'm going to try to do is put my hand, the axis of my thumb, aligned with this carbon, and my fingers will be aligned with priority 1, and they will either curl naturally toward priority 2 and priority 3, in which case my right hand is working because my thumb is aligned with priority 4, and my fingers are curling from 1 to 2 to 3. If my right hand is working in that sense, with my thumb aligned with the H and my fingers curling naturally, then this is an R assignment. Again, clockwise. Right-handed is clockwise. This works. Same general idea working with your left hand. Again, your thumb would be aligned with the H or opposite the H, but what you want is for your fingers to curl from 1 to 2 to 3 naturally. And again, what you're trying to do is you're trying to align the axis of rotation of your hand with the carbon itself that you're trying to analyze, and your thumb is aligned with the H, and then your fingers curl naturally from 1 to 2 to 3 as follows. If your left hand is working, then this is S. If your left hand is working, then this is counterclockwise. This is S. So right hand, my fingers curl 1 to 2 to 3 with my thumb aligned. What happens if I try to use my right hand to analyze something where it doesn't work? Well, my fingers want to curl from 1 to 2 to 3 as long as I orient my hand this way with my thumb toward you. But if my thumb is toward you and the H is back in, then that means that my right hand is not working. That means that my left hand will work. So you can come over here and be like, okay, here my left hand is working, working, therefore this is S. But what I do instead is I simply say, okay, if my thumb is opposite the H, because the H is in but my thumb is out, then that means that my left hand will work and this is S. So you can do it either way. You can do the clockwise, counterclockwise thing. You can use your right hand and your left hand in order to figure this out. Or alternatively, you can do what I do, which is if my right hand works, then this is R. If my right hand is not working because my thumb is opposite the H, then it's S. Illustrating it slightly differently, again, here I would want to have my fingers starting from the carbon to priority 1, which is to say toward you, curling toward the chlorine, which is back into the board, and then around to the F. And so again, my right hand is clearly working, and my thumb ends up aligned, therefore this is again R. As an example of how it doesn't work, my problem is that I want my fingers to curl this way, so they're starting from the carbon toward priority 1, but then they curl toward priority 3, so that means they're not working like that. So what I need to do instead is put my hand this way, and now my fingers are curling from 1 to 2 to 3, and my thumb is down, but the H is up, and so therefore this is not working for my right hand. Therefore, this will work for my left, where I curl my fingers from 1 to 2 to 3, and my thumb ends up aligned. So if my left hand is going to work, then this is S. Again, which one you like to use is entirely up to you, personal preference. I personally prefer if my right hand works because my thumb ends up aligned, it's R. If my thumb ends up opposite, then it's S. That's my personal preference. You need to find the one that works best for you.